We are very, very happy to have Doug Crockford with us today. Of course, he is a very accomplished author. I'm sure many of you have his book, JavaScript, The Good Parts. And there are good parts of JavaScript, but for a real deep insight into that, I should just be quiet and I should welcome Doug out here. So join me in welcoming Doug. Doug, where are you? There, he's over here. Good morning, sir.
Good morning.
These are the Esri developers, and they are eager to listen to you, and you're ready to go.
Let's go.
All right, cool.
So, good morning. Antoine de Saint-Exupéry was an aviator. We used to call pilots aviators back when aviation was really dangerous. It was really dangerous because the planes crashed. Antoine experienced several crashes in his career and survived almost all of them. He was trying to set a speed record from Paris to Saigon, but his plane crashed in the Sahara Desert just outside of Cairo, and he was not prepared for desert survival. So he experienced severe dehydration, he had terrible hallucinations. He was so dehydrated that he stopped perspiring, which is a really dangerous thing to do in the desert. Fortunately, he was rescued by someone who knew how to treat the effects of dehydration, and he recovered. Then World War II starts, and he's exiled to America, where he becomes an author. And he's a brilliant author. He's maybe best remembered for having written The Little Prince. The Little Prince is a children's book about an aviator who is stranded in the desert, who is visited by a strange little boy who lives on an asteroid and is suicidal. Like all the best children's books, it isn't really a children's book, but it's great. And he wrote other books, too, more for grown-ups, which were also really good. He wrote one book about his experiences in aviation, which contains one of the best sentences I've ever seen. It seems that perfection is attained not when there's nothing more to add, but when there is nothing more to remove. Just a brilliant sentence, and I've seen it used in many, many other papers and works in fields like engineering, architecture, design, anything which combines creativity and discipline. He was talking about the design of airplanes, but it really seems to apply to everything. It's just absolutely brilliant. And it applies especially, I think, to software, because we have a requirement in software that programs need to be perfect. Because if a program is not perfect, then the computer has license to do the worst possible thing at the worst possible time. And we don't want that to happen, so we need to make things perfect. And perfection is really hard to attain, but he gives us some insight into how that can be done. I think it also applies to the design of programming languages and could be expressed as the idea of good parts, that we make a programming language better not by adding more stuff to it, but by removing things from it until we make it perfect. So the good parts principle is that if a feature of a programming language is sometimes useful and sometimes dangerous, and if there is a better option, then always use the better option. And this turns out to be a very controversial statement, because there are lots of developers out there who say, I don't want to use the better option. You can't make me use the better option. It's like, why are we arguing about this? And I think it comes from a fundamental misunderstanding. It turns out we are not paid to use every feature of the language. At the end of a project, there isn't a manager with a clipboard asking, did you use a with statement? Did you leave out any semicolons? No, he's not. Did you use plus plus? Excellent. No. We are paid to write programs that work well and are free of error. That's it. So free of error, what's this free of error thing? When did that become part of the deal? Well, it turns out it's always been part of the deal. It's the most important part of the deal, but we achieve it so rarely, it's very easy to forget how important it is. So I recommend to anybody who's doing any kind of programming, learn as many languages as you can. because languages can teach you. And the things a new language can teach you, you can apply then to other languages that you've already mastered. And in my own practice, the language which has taught me the most, surprisingly, was JavaScript. And when I started with JavaScript, I made every mistake with JavaScript that you can make, starting with the first one, the worst one. I didn't bother to learn the language before I started writing in it, which is a mistake a lot of people want to make with this language, and it's inexcusable. There's no reason to do that. So eventually, I decided to learn the language, and I was very surprised by what the language actually did. And that completely changed my understanding, not just of JavaScript, but of programming in general. So, because JavaScript has more bad parts in it than any other programming language, I wrote a tool called JSLint to help me manage that. Because it's so easy in this language to go off the rails, and I needed something to help keep me in the place where the language works effectively. And JSLint, turns out, is a lot smarter about JavaScript than I am. JSLint taught me a tremendous amount about how to think about programming in a way that avoids the creation of error. And JSLint has been extremely instructive to me about how to accomplish that. So I wrote my own book about my experiences with JavaScript and with JSLint, JavaScript, the Good Parts. And the surprising thing about this book is it came out several years ago, but it is still a bestseller in its category, which is really unusual for a software book, because most software books are obsolete the day they're published. And this one is still selling well, and it's because it turns out what I identified as good parts actually are good parts, that there is a part of this language which is effective, and if you confine yourself to that part of the language, you write better programs. So that is still a controversial idea, and there are lots of arguments against confining yourself to just the good parts of a language. So let's review some of those arguments. The first one, it's just a matter of opinion. Good or bad, I might think it's good, you might think it's good, I might think it's bad. It's all subjective. That turns out not to be the case. So I am the maintainer of JSLint, and I sometimes get bug reports from people from all over the world. Someone will write to me and say, there was this weird corner case we had in JavaScript where we spent 2 weeks trying to find this thing. And we eventually found it, and it's just this thing. Could JSLint check for that? And that way, no one else will ever have to waste 2 weeks trying to track this thing down. And if it makes sense, I do that. So if you're using JSLint, it means you will never experience one of those bugs. That's not a matter of opinion, that's a fact. Every feature is an essential tool. I need to have access to every tool in the toolbox in order to do my work. Except that's not true, because it turns out you can write better programs by using only the best tools in the toolbox. You don't need to use the rusty tool with the broken handle. Just don't need to do that. And if you can do better work with fewer tools, then the tools you're not using are not essential. But I need to use this feature because it's sometimes useful. And that sounds like a really powerful argument until you consider that there is nothing which is not sometimes useful. Humans are so inventive and creative, we can sometimes find a use for anything. There's nothing so toxic or disgusting or dangerous that we can't somehow find a use for it. So, because everything is sometimes useful, if that's your argument in favor of a feature, you do not have an argument. I have a right to use every feature. Well, what's happened is we've just changed the conversation. We are no longer talking about what's the best way to write programs, we're now talking about rights. And when you're talking about rights, it's easy to get righteous, and it sounds like, this is important. Except this argument eventually bottoms out at, do you have the right to write crap? So, yes, I have the right to write crap. And at that, is that true? I don't know. It's not important. The important thing is we write good programs that are free of error. We have a responsibility to do that, which I think is much more important than a right. I need the freedom to express myself. I'm a poet, and the way I express my poetry is by leaving out my semicolons. I need to reduce my keystrokes. This is something that affects a lot of us. We imagine that we spend most of our time power typing. And I'm typing a program, da-da-da-da-da-da, except we spend most of our time gazing into the abyss saying, my God, what have I done? What? So if I could give you a magic formula which would increase your keystrokes by a factor of 10 and cut your errors in half, that would be a huge win. You would be so much more productive. Unfortunately, I don't have that formula. But just to give you an idea of how keystrokes are not the thing you need to be optimizing. It's an insult to suggest that I would ever make a mistake with a dangerous feature. Obviously, someone who's incompetent using that would make mistakes, but I am so much better than that, I'm offended. But it's not about you. It's also about the people you're working with. And there are good reasons those features were added to the language. And having watched how the sausage is made, I can tell you that's absolutely not true. So Brendan Eich, who's the genius who invented JavaScript, describes a feature called a foot gun. A foot gun is a feature of a language that you use to shoot yourself in the foot. And he put a lot of them into JavaScript, and I think he regrets it. But they're there, we can't take them out, and there are people who think they have a right to go, boom, look, I almost always miss, watch this. So the purpose of a programming language is to aid programmers in producing error-free programs. That's what they're for. So we used to think that it was not possible to write good programs in JavaScript because the language was so flimsy and problematic that you couldn't write good programs, so there was no reason to even try. Just write slop because that's all it can do. That turned out not to be the case, that not only is it possible to write good programs in JavaScript, it is necessary. It is so easy to go off the rails with JavaScript. JavaScript requires more discipline than most other languages. So there's a lot of confusion about Java and JavaScript still, because they have the same name, right? So what's the difference? It's similar to the confusion between Star Trek and Star Wars. You've got two science fiction franchises with basically the same name, and they both have spaceships and aliens. What's the difference? Well, the fans know there's a huge amount of difference, right? And we can list them. In Star Trek, you've got phasers and photon torpedoes and uniforms and those damn regulations. In Star Wars, you've got lightsabers and blasters. You've got photon torpedoes, completely different concept. Sand, chaos. And it's pretty clear which of these is JavaScript, right? JavaScript is the Star Wars of programming languages. So when you're programming in JavaScript, JavaScript gives you a choice. You can go Jedi, or you can go Jar Jar. So I've observed two things. I've observed the fantasy of infallibility and the futility of faultlessness. The fantasy of infallibility I see mostly in young guys who think they have such mad skills that they can write just crazy stuff, and it's probably going to work most of the time, just writing awful stuff. And then there's the futility of faultlessness. I see this mainly in older guys. People have been doing this for a long time, maybe too long, who's saying, it never works. It's never going to work. Why even try? So two completely different attitudes, but they both end up, surprisingly, at the same place, which is danger-driven development, where you're doing crazy, reckless stuff, taking unnecessary chances, just to keep it interesting. Oh, and don't forget your semicolons. Please do that. So one of the things that makes software difficult to manage is the difficulty of scheduling software. And that's partly due to the fact that we're optimists. We have to be optimists to be programmers, but as a result, we have a really difficult time guessing how much time it's going to take something. And so we don't know how long it's going to take some code, because usually we're writing stuff that we've never written before. But that's just time A. Then there's also time B. Time B is the time it takes to make the code work right. Now, ideally, time B should be 0, right? You write the code, it works, you're done. But that's not how it works. Often, time B is large. Sometimes it's larger than time A. I've seen cases where time B is infinite. That's what happens when a project is canceled after the code is finished because they could never get it working. So in our rush to get things done, we try to minimize time A, but if you do anything in time A which increases time B, you're doing it wrong. We should have a goal during time A to be forcing time B to be 0. That means that we should always take the time to code well. Because sometimes if you're just doing something, a cheap and dirty project, it's only going to happen once, so just be real sloppy. The thing is, even though you're only doing it once and you think you can be sloppy, you still have to make it work. And that's a lot easier if you do it right. So a new version of ECMAScript came out last year, the 6th edition or the 2015 edition. And there are some new parts in it. Some of them are good parts, and some of them, unfortunately, are bad parts. I wish it were possible to only put good parts in it, but it doesn't seem we know how to do that. So there are good parts and bad parts. We still don't have a lot of experience with the language yet, so we haven't discovered all of the goodness and badness, but some of it is clear. So the best new part in ES5 is proper tail calls. So when the last thing a function does is return the result of calling a function, either itself or a different function, the compiler is required to not generate a call return sequence, but instead to generate a jump. And that is a little bit faster, and it also enables new styles of programming like continuation passing style, which are really, really great. So there are new forms of programming that'll be possible because we've got proper tail calls. With proper tail calls, JavaScript finally becomes a real functional programming language. We have the ellipsis operator, which allows us to have a much nicer way of dealing with functions that take a variable number of arguments than we had with the old arguments array in JavaScript, which never worked very well. So here we have two versions of the curry function. They both do exactly the same thing. The top one is the way we can write it in ES6. The bottom one is the way we write it in ES5. The ... means any number of things can happen here, which is brilliant. Very, very light, very nice, so much better than the other one, which is doing a whole lot of stuff which has nothing to do with the curry function. We've got modules, which is good. Modules allow us to have independent bodies of code which have strong interfaces. That's something we need for writing reliable software. That should have been in the language from the beginning, but we finally have it now. Unfortunately, the new module syntax is way too complicated, but there is a subset of the module which I think is adequate, and I recommend using that subset. We have let and const. Let is like the var statement, except it respects block scope. Now, it turns out we don't need block scope, but it's good to have block scope because all the Java guys want to be doing block scope, and they just don't understand anything else. So I'm going to recommend that we stop using var, everybody use let, so that the Java guys stop getting confused. Then we have destructuring, which is a shorthand notation. It doesn't allow us to do anything that we couldn't do before, but it affords some nice patterns. So here we've got let that and other, which are surrounded in curly braces, equal some object, and that is short for that equals some object dot that and other equals some object dot other. Again, nothing we couldn't do before, but there are some interesting patterns, and I'll show an example of one in a minute. Then we have weak maps. Weak maps are great. Weak maps are the way that objects should always have worked in JavaScript. Unfortunately, there was a design error, and in JavaScript, the keys of an object have to be strings. They can't be any other type. And there's some programs that really need to have other values, especially objects and things. And weak map does that. Unfortunately, we didn't fix the way objects work. We added another thing instead. So instead of repairing the language, we made the language even more complicated, which is a problem. But the worst problem with this feature is it has the worst name ever put on a programming language feature. Make weak maps. Who wants to put something weak in their program? But they're really good. And there are things we can do using weak map that we cannot do in the language without weak map. Then we have megastring literals. We now have string literals which can do interpolation and which can span many, many lines. So there are some things that we can do with that. We've always had regular expressions in JavaScript. This is a regular expression that matches the number of literals that are in ES6. And the thing that I hate about regular expressions, at least as practice in JavaScript, is all the components have to get all mushed together. And so that's unreadable. Very few humans could make sense out of that and recognize what it's going to match and what it's going to reject. But we've got these new megastring literals. So I'm going to make a function which will pass a string to the regular expression constructor, and I will pass that string to it, removing all of the white space from it. And then I will make a megastring literal, which is exactly the same as the one on top, except now I can put spaces in it and line breaks and stuff. And now you can kind of see what's going on here. I can have 0 followed by a B for a binary literal, or O for an octal literal, or X. We've always had hex literals, or a decimal point, and so on. So this, I think you can make sense out of. Or you could just ask, which of these two forms would you rather maintain? But still, regular expressions are pretty scary. So there's a tool on the web called Regulex. I highly recommend this. You paste a regular expression literal into it, and it will produce a railroad diagram of what that regular expression does. So you can get a graphic view of what it is, which makes it possible to make good judgments about what it's going to match, which is great. I will never write another regular expression without using Regulex. We have a new format for making functions. There was a complaint about ES5 that the word function was 8 letters, and that's too much. I said, well, there's this new thing called keyboard macros. And they said, well, it's too much to read. Oh, okay. So we've got this new fat arrow or fart operator. So we can see we've got the parens, which introduce a parameter or more parameters separated by commas, and it will return whatever is on the other side of the fat arrow, which can make certain kinds of simple little functions which just compute one expression and return the result much nicer to write. Unfortunately, there's a syntactic ambiguity in the way that they were defined, so that this particular one does not do what it looks like it should do. It's not going to return a new object with an ID property whose value is the name. Instead, it is going to return undefined, which is surprising and odd. And for that reason, I'm not a big fan of this. There was a chance to get it right, and we got it wrong, which is unfortunate. We keep adding these weird, ambiguous forms into the language. Class, I am certain, is by far, without question, the worst bad part that we added in ES6. It was also the most requested new feature, and it was requested mostly from Java programmers who are being forced to work in JavaScript because that's where the jobs are, but they don't want to learn JavaScript, and so they wanted to have this class syntax added to the language so that they didn't have to learn anything. And we added it, but it doesn't actually add classes to the language. It is syntactic sugar on top of the prototypal inheritance that the language always had. And so in some cases it works as you would expect, but in the corner cases it doesn't work at all as you would expect. So it's going to invite some confusion. And also it's a distraction, because the best thing about JavaScript is the way that you use functions. When you understand how functions work in JavaScript, it completely changes your mind about everything, and it's great. And you find you become much more productive and much happier about the programs that you write. So the people who buy into class are going to feel vindicated and justified that it's in the language, therefore they have a right to use it, and they will go to their graves never knowing how miserable they were. So it's been a while since I wrote the book about the good parts, and since then the language has gone through 2 revisions. So I thought maybe I should look at the book again and look at, have I changed my mind on what was good in the original publication? So in the book, I recommended not using new, using object.create instead. And in fact, I managed to get object.create added to the language just so that I could use it. So I was really surprised when I noticed that I had stopped using object.create. It was in there just for me, and I'm not using it. And the reason I stopped using it is because I stopped using this. And the reason I stopped using this was because of a research project I did a few years ago called AdSafe. In 2007, there were a number of research projects that were trying to figure out how to produce a safe subset of JavaScript so that we could have safe third-party interactions. There was FBJS at Facebook, there was Web Sandbox at Microsoft, there was Kaha at Google, and my own AdSafe project. And one of the difficult problems we all had to solve was, what do you do about this? In fact, just having this in the language makes it harder to talk about. Which this are we talking about? It's like pair programming with Abbott and Costello. But I'm talking about, I'm doing that, so I must be talking about this. So the problem with this is if this is in a method and you call the method, this gets bound to the object of interest, which is exactly what you want. That's object-oriented programming. But if you call that same method as a function, this gets bound to the global object, which gives away all of our security. And how do you deal with that? So the approach that the other projects took was to have code rewriting. So they would have a compiler which would read in JavaScript and write out JavaScript, and the JavaScript written out would have lots of runtime checking and indirection added to the code. So the code they produced was much bigger and uglier and slower. The approach I took with AdSafe was, if this is in the program, then the program is illegal, and we reject it and we're done. And we don't need to make any transformations of the code. And as a result, existing code would run at the same speed, it'd be easy to debug, everything's great. The problem with AdSafe was that the percentage of existing code on the web that would pass the AdSafe rules was 0%, because everybody is using this. And so as an experiment, or my premise was that if you take this out of the language, what you're left with is a functional programming language. And a functional programming language is Turing complete, so everything you ever need to do, you can still do. So I started writing in that subset, in order to determine how painful is it going to be. And I was really surprised to discover it got easier, that my programs were smaller and faster and nicer, and it wasn't painful, it was really pleasant. And so I'm not using this anymore. I don't recommend anybody use this. Functions, that's where you want to be, functions. I stopped using null. JavaScript has 2 bottom values, null and undefined. And there's some argument that programming languages shouldn't have any bottom values, but everybody agrees there should never be more than one of them. And JavaScript has two. And they're used interchangeably, which is a problem because they are not interchangeable. They are actually distinct values with some different properties. And when you use them interchangeably, there's the potential for confusion to occur, and confusion causes bugs. So I've decided to stop using null. I use undefined instead because that's the one that the language itself uses, and it also avoids the type of error with type of null. I stopped using falsiness. The idea of falsy values was added to JavaScript in order to allow you to write some of the idioms that you write in C. C is kind of a weakly typed language, so it uses the same value to represent 0 and the null character and null and a few other things. And so if you just say if something, then if it's not 0, you take the true branch, otherwise you take the else branch. And JavaScript tries to capture that idea, but it turns out to be a really bad idea. And it bifurcates possibility space in a weird way. So I recommend in your if statement, always have a Boolean value there. Don't rely on a bullish value. I don't use for anymore because ES5 introduced array.forEach. So you take an array and provide it a function, and it will call that function being passed each of the elements of the array. Having that, you don't need for anymore, and that's great. So I like that a lot. I don't use for in, which is the technique that JavaScript provides for iterating through the keys of an object. For in has bad problems where it'll dredge up stuff from the inheritance chain, and you start seeing methods, which usually are not what you're looking for. So I managed to get object.keys added to the language, which returns a nice array of strings, and then you can pass that array to for each. ES6 will have proper tail calls, and at that point, I will stop using loops entirely. No more loops. I'm just going to be using functions. So to illustrate, here are two versions of the repeat function. The repeat function takes a function as an argument and will call that function until it returns undefined. One of them is written using a while loop. The other is written using tail recursion. In ES6, these are both required to run at the same speed with the same memory pressure. So there will no longer be a performance advantage for using iteration over recursion. So from this point on, I'm just doing recursion because I like functions and I don't like loops. So I've been thinking a lot about the next language. What's the next programming language that's going to replace JavaScript? And I have to believe that there's going to be a next language because if it turns out that JavaScript is the last language, that would be really sad. JavaScript can't be the last. Think of our kids, right? We have to give them something better than that. So I've been thinking about the next language. What's it going to look like? What's it going to be like? What's the paradigm? What's it going to do? What are the signs? How will we recognize it? It's sort of like watching for the Messiah. You know, how will we know? The one thing that I'm certain of is that when it finally does appear, we will reject it out of hand because we always do that. And the reason we do that is because we are as irrational and emotional as normal people. It's true. You wouldn't think so to look at us, but we are. And so here's my evidence for why I would say such an insulting thing, comparing you to normal people. It took a generation to agree that high-level languages were a good idea. When languages like Fortran first came online, everybody was writing an assembly language. An assembly language is really tedious. You're programming every individual instruction, extremely error-prone. The idea with Fortran was they called it automatic programming. It's not even programming anymore. You just express the formulas that you want to write, and it translates them for you, and you're done. And you can be so much more productive. And the programmers at the time, most of them refused to accept it. And they had lots of reasons that We can't afford the loss of performance. It's going to slow us down. We need more control. We're giving up too much. Where, in fact, they would have benefited quite significantly. Then it took a generation to agree that GoTo was a bad idea. Dijkstra publishes his letter in the CACM in '68, I think, and that starts an argument that goes on for 2 decades. And it's a really violent, irrational argument, but it went on for a long time. And eventually we figured out that structured programming was the better way to do it, but we had to argue for 20 years. It took a generation to agree that objects were a good idea. So objects were first spotted in a language called Simula, which was developed in '67 in Norway. A really important, significant breakthrough, and nobody recognized it except for one guy, a grad student at the University of Utah, Alan Kay, who thought that this idea of objects was so powerful that it could be used in a programming language for children. That was that powerful. So he spent a decade working on a language called Smalltalk. And Smalltalk was the language that brought the idea of object-oriented programming to the mainstream. Then the industry had a choice. We could take Smalltalk 80, which I think is the best designed programming language in history, or C++. And which one should the industry go with? And the decision was made by people who fundamentally did not understand what object-oriented programming was, and they chose C++ because you didn't have to understand what object-oriented programming was in order to use C++. And that set the direction for the industry, and all of the object-oriented programming languages since then have followed in that same pattern, away from the Smalltalk thing toward other stuff. And then finally, it took 2 generations to agree that lambdas were a good idea. Lambdas were discovered at MIT in the early '70s in a language called Scheme. Brilliant, brilliant thing. I think the smartest thing ever discovered in programming. And as always happens, the world took no notice of it at all. And that one took not 1 generation, but 2 to finally catch on. And it's catching on now. And what's surprising is the language that brought this idea to the mainstream was JavaScript. JavaScript was the first language to take the schemish idea of lambdas, called them functions, but it's the same idea, and bring them to the mainstream. And it was quickly followed by Python and Ruby, and then C#, and finally Java figured out how to do it last year. And the reason it's happening is because the kind of programming we're doing is changing. We're now doing distributed stuff, distributing on the small scale and distributing over the cloud. And functions provide a much better way of managing that. So in thinking about programming languages, I want to put them into 2 distinct categories: systems languages and application languages. System languages are languages that you'd use to write a kernel or a memory manager, a device driver, something that needs to be really close to the metal, and nothing else. Everything else should be written in application languages. We need new system languages because the dominant system language is still C++, or I'm sorry, C. C comes from the '60s. I mean, it's a really old language. We have lost the ability to innovate in systems languages. But I'm more concerned with the application languages because that's where all of us live. And so I could take the class of application languages and divide them into 2 broad classes. There's the classical school, which is C++ and Java and C# and almost everything else, and the prototypal school, which is pretty much just JavaScript. And for a long time, I was a big advocate of the prototypal school because it had a lot of advantages over the classical model. Because in the classical model, it requires that you do classification, where you look at each of the objects in your system and determine what they are and what they do and how they relate to others and put them into classes. And then you do the taxonomy, in which you try to figure out how are all the classes related to each other, what's going to inherit what, what's going to implement what, and so on. And it's really, really complicated, and it's usually done at the phase of a project when you have the least understanding of what the correct taxonomy is at the beginning, when you don't know. And so inevitably you make mistakes in the way you design your class hierarchies, and you start to recognize those mistakes in that things don't compose correctly, and you start wishing that you had multiple inheritance because you just can't get the thing that you want. And the breakage that you put in those initial classes seeps its way into the upper classes that are built on top of it. And eventually you're forced to refactor, which is a really scary thing to do because it means you have to tear everything apart and it might not go back together again. And when you're working in the prototypal model, because we have less dependency on things, eliminating that dependency means those problems just don't occur. And so it's a much simpler model. So I used to be an advocate of prototypal inheritance. So looking at the benefits, the primary benefit is memory conservation. By using object.create instead of object.copy, it means that all of the instances can inherit stuff, and that reduces the amount of memory that needs to be allocated to each object. I think that might have made sense in 1995. But it doesn't make so much sense now, because Moore's law has given us so much memory that trying to save money or shave memory off of objects is just not worth it, not a good return on investment. And that's the only advantage. It comes with some disadvantages. There's confusion because owned properties don't work exactly the same as inherited properties, and any source of confusion is inevitably a source of bugs. It also provides for a retroactive heredity, that you can change what an object inherits after an object is constructed, which I think is a really dangerous thing. And it's built into the model. And that inhibits performance. JavaScript engines go fast by making assumptions about the shape of objects, but they have to be pessimistic about prototype chains because what is inherited from a prototype can change at any time, so it actually degrades performance. So I used to be an advocate of prototypal inheritance. I am now instead an advocate of class-free object-oriented programming. And that's why I think this language is interesting and worth learning. I think class-free object-oriented programming is JavaScript's gift to humanity. So let me explain how this works. We'll start with block scope. Here we have two blocks using the let statement. If you're familiar with the idea of block scope, you know that the inner block can see the variables of the outer block, but the outer block can only see its own variables. And we can and we can also do this as a function, right? We can have two nested functions, and the inner function can see the variables of the outer function, but the outer function can't see the inner function, because a function is just a block with a little extra mechanism which allows you to defer the execution of that block until sometime in the future when you do the invocation. And we can express the relationship of these variables and these scopes as a Venn diagram. So here we have the variables that are visible to the outer function, and these are the variables that are available to the inner function. And we can see that the inner function closes or encloses the variables of the outer function, and that's why this is called closure, which is unfortunate because the word closure really confuses people, because they think closure means retribution or vengeance. And that's not what we're doing here necessarily. But that's what it is. And I think this is the best idea, most important idea in the history of programming. And this is the thing that JavaScript brought to the mainstream. And the reason it took 2 generations to bring this to the mainstream was that language developers didn't know how to solve this problem. What if the inner function survives the invocation of the outer function? So in this case, we call the green function. It allocates A on the stack. It returns a yellow function. And in returning, the A is removed from the stack. Now, at some later time, we call the yellow function, and it wants access to the A variable, but the A variable is no longer on the stack, and everything blows up. So that was an insolvable problem. How do you solve it? You get rid of stacks. You just allocate all the activation records on the heap. You got a good garbage collector. It's trivial, really, really easy. So that's what we do now. And all the languages have figured out how to do this. So using that idea, this is how I recommend making objects in ES6. I've got my constructor function. I wrote it with a lowercase c because it doesn't need a new prefix. I'm going to pass in a specification object. And the reason for that is, years ago I wrote an API that was really terrible. I had a constructor that took 10 arguments. And the problem with that was no one could remember what order they went in, so it was causing lots of trouble. And then it turned out nobody ever used the third argument, but we couldn't take it out without breaking all the code. So we were just stuck with it. If instead I'd said, you pass in an object literal which describes what you want to make, then we get named properties. And it doesn't matter what order they're in, because the name is what determines it. And we can have good defaults for names that you don't provide. And if it turns out names become unnecessary, we can simply ignore them. So I recommend that for constructors. Also, that means that you might have a JSON payload, and you can pass that directly to a constructor and use that to reconstitute objects. Then I'm going to use a let statement with the new destructuring syntax that I showed you earlier to copy values out of the specification object and use them to initialize variables that have the same name. So let.memberSpec means the same thing as let_member equals spec.member. So we have sort of a declarative form which says create variables with these names separated by commas that are initialized by values from the specification objects with the same name. Then I can call another constructor function which can take the same specification object because we can union the specification parameters. And I will then copy all of the methods that it produces that I need into my own local variables. And because I'm copying these things out, it solves the banana problem, where you want to inherit a banana, but you also inherit the gorilla that's holding the banana and the whole jungle. Now you can inherit just .banana, so that's nice. And you can also call as many of these as you need, so it gives you a form of multiple inheritance if you need it. Then we create our own methods. Each method goes into a variable. And because of the closure thing that I just showed you, that method will have access to all of the member variables, all of the other methods, all of the methods that we're defining, and the specification object, and this method does not use this. Then the last step, I'm going to return a new object, and I'm using some new syntax here. If I have an object literal with just a name, comma, and a name, that is short for method colon method, comma, other colon other. So it looks more like a declaration list where I'm declaring what all of the public methods are going to be. They just go into the object. And then the last step, I'm going to freeze the object so that the object is now completely immutable. It cannot be tampered with or modified, but the dynamic state of the object is being held in the closure, in the member variables. And so we can continue to modify them, but only through the methods. This is the only way in JavaScript to get objects with this property, where we can have really strong interfaces which defend the values that are in the object. So in object-oriented programming, we started with Pascal records, or C-structs. You got a data structure with named properties, and associated those objects with methods that could act on them. And I think that was an important and necessary step in the evolution of programming, but it should not have been the last step. So I'm proposing we go one step further, and we now have two completely distinct kinds of objects. We have simple mutable objects that contain only data, and we have immutable objects that contain only methods that act upon that data. This gives us some very nice reliability properties and security properties, which I think we need and want. So I made a bug in 2001, and I need to confess. So I was writing a JSON parser in order to demonstrate how easy it was to write a JSON parser, and in it I included this statement. I was creating a variable called index, and its value was an int, or its type was an int. And its use was to count the number of characters we were into while we were parsing a string or a stream, so that if a syntax error occurs, we can report where it happened. And at the time, I thought about, well, what type should that be? And I made it an int because an int would allow us to have text that were 2 gigabytes, which was a big disk drive at the time. And I'd never had a JSON text that was bigger than a few K. So I thought I was future-proof. I was looking way, way ahead. Until a couple of years ago, I got a bug report from somebody who said that they were trying to parse a JSON text that was several gigabytes in size, and it contained a syntax error past 2 gigabytes. And my parser produced a wildly incorrect position for where the error occurred. They immediately figured out what the problem was, and the problem was that I used an int. And the problem with ints is that they overflow. And when they overflow, very, very bad things can happen. And tests cannot find these sorts of bugs, because your tests will always assume that everything is the right type. And so there's no way to test in a way which violates those assumptions. The problem with ints is what happens on overflow errors. So you could ask, well, what should happen? If we have a number that's too big to put into a cell, what should happen? And there are a number of possible things you could do. One would be the machine halts. That's sort of an old school idea. You'll never get to 5 nines that way, but you'll never make mistakes, and that used to be considered really important. Another approach might be we raise an exception and say that didn't work and force some other software to handle it. That's a reasonable thing to do. Another thing might be we'll substitute some NaN value, some not a number value, so that when you actually go and look at that cell again, that cell will tell you, I don't know what you're looking for, but whatever it is, it ain't here. Another thing you might do is take the biggest number that does fit and put that in there. That's called saturation. And that's a reasonable thing to do in signal processing and computer graphics, but you don't ever want to do that in financial applications. But if instead your goal is to maximize the likelihood and the severity of errors, I think what you would do is throw away the most significant bits and don't tell anybody. And that's exactly what we do. So why is that? It's because in the 50s, computers were made out of vacuum tubes. And vacuum tubes were big and heavy and expensive. They consumed a lot of power. They created a lot of heat, and they didn't last for very long. So the more tubes you had in your system, the more expensive it was to build and operate, and the shorter the mean time to failure, which was something we used to have to worry about. And then some genius, and I do believe it was a genius, figured out that if we used complement arithmetic instead of signed magnitude, then we don't have to implement a subtract circuit. All we have to do is complement the input to the add and ignore the overflow. This is brilliant. And so they did that. Now, we don't use tubes anymore, and Moore's law has given us more gates than we can imagine, but we are still designing machines like it's 1950. We can't stop doing it. And to make it even worse, ints come in a lot of different sizes because memory used to be really expensive, and how many bits you allocated to a variable used to matter a lot, but it doesn't anymore. But our languages think we do. So you look at Java. In Java, you've got byte, char, short, int, long, float, and double. It means that every time you allocate a new variable or a new property of an object or a new parameter, you have to ask, which one of those? And if you pick the right one, then your program will work. And if you pick the wrong one, it's going to fail. And it's probably not going to fail in your tests, and it's probably not going to fail soon. It's going to fail sometime in the future, probably in a time when you really most don't want it to fail. And it's a waste of time, because the time you spend deciding which one is much more valuable than the value of the bits that you saved. The bits that are saved and going to a shorter type are worthless, because you've got gigabytes of RAM in your pocket. I mean, you can't imagine how many bits that is. It's just, and trying to save, well, I saved 8 bits there. It's just not worth it. There's no benefit. Now, JavaScript, on the other hand, got this right. JavaScript has one number type, which means you cannot make a mistake by choosing the wrong number type. That's a hugely valuable thing. Unfortunately, it's the wrong type. Yeah. And the reason it's the wrong type is because of this. This is the most reported bug in JavaScript, that 0.1 plus 0.2 is not equal to 0.3. It's almost equal, but not, and that matters when you're adding up money. And it matters in other situations too. So we have a number type which is confusing and weird, that doesn't produce obvious results. And why is that? Well, again, we have to go back, let's go back to the 40s first. So when the first von Neumann machines start coming online, they are integer-only machines, but they're doing scientific and mathematical calculations, so they need to figure out how to deal with real numbers. And they start by doing scaling arithmetic, which is really hard. And then some really smart guy figured out that if a number is actually two numbers, one is the number and the other tells us where the decimal point is, so we can move the decimal point around and let the subroutines handle that, then programming gets a lot easier. And this is called floating point. And so in the 50s, when we start mass producing machines, there's a desire to make it faster. So can we put floating point into hardware? And some genius, and again, I believe he was a genius, figured out that if we make the basis of the numbers base 2 instead of base 10, then we don't have to do a divide by 10. We can do a shift by 1, which is essentially free. That made so much sense. So in scientific computing, in Fortran, that's the way they go. But that doesn't work for the business guys, because, again, they're adding people's money, and you can't be approximate when you're dealing with money. You have to be exact and precise. So they have their own machines for doing their arithmetic. They're using binary coded decimal so that they can get everything correct to the last decimal place. And they have their own languages like COBOL for doing that. So when you ordered your mainframe, you could order the optional floating point unit or the optional BCD unit. But then Java happened and COBOL failed, and now we're doing all this stuff using the scientific numbers, which doesn't work for most applications. So I propose to fix it. And this is my fix. I call it DEC64. It's a 64-bit notation for numbers. I have a 56-bit coefficient, which is just an integer, and an 8-bit coefficient, which is the coefficient, or the exponent, and the value of a number is the coefficient times 10 to the exponent. And so this works the way you would do arithmetic on paper. It does arithmetic the way you learn to do it in school. So it doesn't have all the weird surprises that you get from binary floating point. It matches your expectations very closely. It reduces an important source of error. And we can get efficient implementations of this. So I've written a reference library in x64 assembly language, which demonstrates this stuff. It can add 2 ints in 5 instructions, which is pretty good. It's more than 1, which is the ideal, but it also gives you protection against overflow, and it also gives you nans, which are 2 nice things to be able to get for 5 instructions. And it would be capable of having hardware implementations as well. So my goal is to try to convince everybody in the world that from now on, all application languages should only support this number type, because this is a number type that works for people and works for money and everything. And you can do the science with it just as well, with fewer surprises. Now, it sounds kind of audacious trying to convince everybody in the world to do something, but I actually have a little bit of experience with that. But in this case, I don't have to convince everybody in the world. I only have to convince one person. And that's the man or the woman who designs the next programming language. If I can convince that genius that they want to have one number type in order to prevent errors and to be one that works really well for human beings, then we win. So I'm the guy who did the JSON data interchange format, the world's best loved data interchange format. And I did not intend for JSON to be the last data interchange format. I just needed something to solve a particular client-server problem, and it works really well for that. But it is going all over the place. It's become very popular. So this is Google Trends showing interest in JSON versus XML. XML is the red line. We can see the world has steadily been losing interest in XML since 2005. And JSON's been very quietly growing up. And there's been no machine, there's no JSON industry. JSON works because you decided this was a whole lot easier than the alternatives, and you were right. And that's what's going on. And I can't predict when those lines are going to cross over, but Google can. So we expect sometime this year, JSON becomes officially more popular than XML. So I did not intend for JSON to be the last one. But, you know, it works really well for what it was designed for, but it's doing a lot of other things, and so there's pressure on JSON to change. So I have some advice to anyone who is thinking about producing a new standard. Number one, please don't break JSON. Don't recommend that we change the JSON standard. The JSON standard does not contain a revision number, so there is no mechanism for revising it. So we're stuck with JSON the way it is, which is actually great because it means that there is one thing in the stack which will never change. You know, everything below, everything above can change, but the JSON layer will always be the same. And having one bit of stuff, even if it's not perfect, being guaranteed to be that resilient, I can't think of any feature that we could add that's more valuable than that. So make a new thing. And if you make a new thing, make it significantly better. Don't be JSON plus one little thing, because if it's JSON-like but different, or if it's even completely different, there is going to be a compatibility tax that the world is going to have to pay. So make it worth it. Add enough value, justify the conversion or the cooperation, the coexistence. And please give it a better name. The worst thing about JSON for sure is the name. For one thing, people aren't even sure how to pronounce it. I've been saying JSON, most people say JSON. It turns out the correct pronunciation is JSON. Everybody? And I hear from guys named Jason all the time. You know, I'm in the office and I hear Jason, what? I said, Jason, if you're here, I'm really sorry. I don't know what I was thinking. I mean it, man. I'm really sorry. And JSON is by far the worst part about, or the name is the worst part about the thing. It stands for JavaScript Object Notation, and almost everything about this is wrong. We start with JavaScript. We already talked about how the word name JavaScript is confusing. And then having JavaScript in here, I did it as an homage. I was trying to give credit to where the idea originally came from. JSON is just taking something that already existed in JavaScript, defining it precisely, and making it available for other applications. The JavaScript standard does not define JSON. The JSON standard does. But there are people who think because JavaScript is in the name, they get confused about that. Whenever you have confusion, bad things happen. Then the word object represented the way that JavaScript thinks of objects, just a loose container of key value pairs. But other languages, object means something very different. And so people get confused by, well, that's not an object, that's a hash table or whatever. Notation is okay. I don't see a problem with that. So if you want to call it notation, that's okay. But you can probably come up with a better name than that. So that brings me to the end. I'm very happy to be in Palm Springs with all of you this week. It's been great. And thank you, and good night.